This next video in the sequence of 3 bottom process tutorials is going to focus on stresses on the bed. So this is examining the computing the magnitude of hydrodynamic forcing that leads to the sediment transport, or can lead to sediment transport. Again, I want to note that it is a true coupled problem between the hydrodynamics and the sediment, because the hydrodynamics from the currents, here we're looking at a boundary layer, and the wave-driven response on the seabed, which is generally rough, can generate bed forms like this, and those bed forms then influence the nature of the flow above it. So it is a coupled problem. It is a two-way problem that we have to distinguish, and that's something that makes sediment transport in terms of modeling quite difficult, coupling between the two processes. We've discussed the idea of a turbulent boundary layer before, speaking both in terms of the atmospheric boundary layers as well as the bottom boundary layer. We have a turbulent flow over the bottom, and one way of looking at that in an ideal sense is in terms of what we call a logarithmic turbulent boundary layer, or law of the wall. In that sense, we're thinking of the boundary layer, and this is the distribution of velocity above the bottom. We have the no-slip condition at the bottom, so we have zero velocity, and a greater velocity at some distance above the bottom. A 3-layer system is a way that's commonly looked at. You have, on top of all this, let me just sketch what the actual boundary layer might look like if we were to go out and measure it. And again, this is in the Reynolds average sense, and it's something discussed by Miles. This idea that there's lots of little small-scale fluctuations happening on the order of seconds and less, but if we average over those, you get a kind of mean profile that looks something like this, the red line. And that's composed of 3 different parts. A laminar region down here. The thickness of that laminar region is generally about 10 times the grain size, or 10 times D50. That's a rough approximation. And there, you're so close to the bed that essentially the larger eddies can't get anywhere near the wall, and so it suppresses the turbulent motion that lives there. Then you have a stretch of space. I didn't do a very good job drawing this line. Stretch of space, which we call the actual, which can be defined by this logarithmic wall equation right here, and this is the log layer stretching from between the dashed lines. In here, the velocity is a function of the vertical coordinate, can be described using as the natural logarithm of the ratio of the vertical coordinate to z0, which is the hydraulic roughness, which I'll define in a second. Hydraulic roughness is we can directly relate to the actual roughness, and the roughness in the bed comes from the grains and biology that lives in there. So we can define these log laws in this nice non-dimensional sense. K is von Karman's constant, which I define here, 0.40. Some people think it's 0.41, doesn't really matter. And U star is what's called the friction velocity. It's a non-dimensional velocity that is related to the stress, but I won't go through that. It's not important. Important things we can collapse all these different turbulent log layers into a single logarithmic distribution from essentially any place. This log law is good about half the water column in a typical shallow water flow, and then you have this outer layer which doesn't really correspond with the log layer out here. But it's a pretty handy way of essentially defining the distribution in the water column. And what you can do is go out and measure the water column, assume it's a log layer, and that will allow you to derive either Z0 or U star, these kind of quantities. If you know U of Z, you assume it's a log layer, you can get at these other quantities. A key thing is getting at U star, which allows you to estimate the local stress. Stress is hard to measure, but if you can measure the velocity profile, you can make estimates of stress. And that is what some people do. This hydraulic roughness Z0, it's not a physical length scale, but it is a length scale. And essentially, it defines where the turbulent law would go to 0. So it defines a distance out from which, across which you really have a laminar subregion. That laminar subregion is a thickness C0, and we have, generally we relate it to the median grain size, D50 discussed in the previous subunit, divided by 12, or basically a tenth of that D50. So the hydraulic roughness in certain flows is established by the physical roughness. These are cases where the physical roughness itself sticks out into that turbulent log region. For hydraulically smooth flows, like muds for example, that physical roughness is just confined inside this laminar sublayer. It doesn't reach across into the turbulent zone. It's not interacting with the eddies that are up there, the physical roughness. In that case, the hydraulic roughness only depends on these flow characteristics within the boundary layer. It doesn't depend on the physical roughness of the flow. The bed shear stress, it should look a lot like our atmospheric shear stress. So again, the stress we assume in most cases related to velocity squared, some kind of velocity squared, a drag coefficient, no dimensions at all, and then you have your fluid density here, roughly 1,025 kilogram per meter cubed for seawater. Now this is the way this is typically written, and so and U is can be different characteristic velocities, and in most cases we're thinking about the vertically average velocity for a shallow water system. So this U bar, I put a bar over it indicating it's been vertically averaged. CD is the drag coefficient. Now the drag coefficient is related to the roughness. Rougher bottom has higher drag. This is one of the reasons you want to keep your boat smooth. This is von Karman's constant sitting in the numerator here. If you plug in some values, for example, if we were to use H equals 1, depth of 1 meter, Z0 corresponding to a grain size of about 1 millimeter, which is a coarse sand, we would get a drag coefficient pretty close to that. I think that works out to about 0.0021, so it's very close. So this is a typical value you could plug in if you don't have better information. Oh, actually I put some numbers in here. So if we have a 1 meter per second vertically average flow, and we make this assumption about the CD, then we can come up with the stress. This is a pretty strong stress here, 2.5 newtons per meter squared. Another name for a newton per meter squared is a Pascal, PA. That's a units of stress in our KGS system. That's important because the sediment's responding to that stress, and how big that stress is will help us decide what the sediment's going to do. Is it going to sit there? Is it going to be dragged along? Is it going to be suspended, etc.? Waves also influence the seabed in a bit of a different way, though, because remember, if you're sitting here, as the wave passes by, you're experiencing these orbital velocities, a flow to the right, then a flow to the left. And that orbital velocity circulates once per time period, where that time period is equal to the wave period, so the forcing is the same. Now near the seabed, and we're assuming shallow water waves, so the waves themselves are influencing the seabed, and that was discussed in a prior lecture. And the velocity very near the bottom here, UW, is related to the wave height. Capital H is the wave height, little h is the depth of the fluid, T is the wave period, and K is the wave number, inversely related to the wavelength. From this we can calculate a near bed wave orbital velocity in meters per second. We can also get it, what is the excursion distance, right? So if we have a neutrally buoyant particle, and this is in a wave tank, and we have a video camera, we'll see it moving back and forth. What is the physical extent, length dimension, over which that is oscillating every period? And that is A, this constant A. A stands for an amplitude, but it's essentially it's the excursion distance of that particle. This just comes from periodic motion. If we have periodic motion with a max velocity of UW and a period of t, then the excursion distance is UT over 2 pi. So that allows us to calculate the excursion distance in meters. Both these parameters are important in terms of deducing the stress on the bed from these waves. Now waves go back and forth and back and forth. So if we consider the boundary layer that the current generates, we consider that establishing itself over a long time. So starting from rest, the fluid starts to move from a pressure gradient. The bottom acts on the fluid to slow it down, and internally the friction on the inside of the fluid starts to slow down the layers above that, the layers above that, the layers above that, and ultimately this distribution of friction in the water column, which is established by the turbulence, will establish the resulting profile in reaction to that pressure gradient over a long term. We don't have a long time for the wave boundary layer to set up. Wave periods in typically near shore can be seconds. Far offshore, we're talking tens of seconds, and over that time the flow is going to the left and the flow is going to the right. This shows a series of velocity profiles measured in probably a wave tank, I can't remember, as the waves are moving back and forth, and you can see that it is setting up little boundary layers. So at time t equals 0, say the wave, we're in this neutral point here, and then the flow is moved, the wave-induced flow is moving to the right, and it starts to set up this boundary layer. The biggest one seems to be out here, and then it moves back again, and now the flow is moving to the left, and it's this is a wave-driven only flow, so there's no net motion, and you have, at the furthest extent, you have this one here. So these little, it does generate little thin boundary layers on the bottom. These are this is millimeter scale here. So you're talking about a wave boundary layer on the order of millimeters compared to a current boundary layer, which can be on the order of meters. That is because there's simply not enough time to set up the boundary layer. So it's confined to a thin layer, and that means even though the velocities might be weak, the stresses can be big because the velocity is changing rapidly over a very short distance. Again, we set up a quadratic stress relationship. The stress from the waves on the bed is related to the density of the fluid, some kind of drag coefficient, here we call it a friction factor, but that's a drag coefficient, and a characteristic velocity, and that's that wave velocity at the bottom squared. So we keep seeing that theme again, that stress is dependent on the density and the fluid velocity squared times some kind of factor. And that factor here is a friction factor. There are, as I put here, many empirical formulas. The world of wave dynamics, in particular sediment dynamics, the physics is very complex. There aren't really closed form solutions. A lot of it depends on a mix of physics and empirical formulations, and you sort of pick and choose from experience. So I put the formulation of Soulsby up here. You can see it's related to the hydraulic roughness and this wave excursion. So both of those are length scales. So this is a non-dimensional number, and you see, whenever you see a complex exponent like this, it smells like an empirical formula. Physics doesn't like to produce a 0.52 or a 1.93. So this allows you to calculate the stress from the waves in the bed. Of course, this is a what am I trying to say? This is just the friction factor to get at the drag coefficient. The stress we can get at here, this is the average stress over the wave cycle. You have stress from currents, and these two things can often be acting together. You have a harbor, tides are coming in and out, and on top of that the wind's blowing, so the waves are moving in one direction. So you have waves and currents at the same time. Both of them are generating stresses. We looked at the independent formulas for calculating those stresses on the bed. However, when they act together, the two of them act in a nonlinear fashion, which is all based on this classic work of Grant and Madsen dating back to the late 70s, looking at the nonlinear relationship between them. And there's a number of ways to actually define this. I put Soulsby's formulation here. There's a great book. I'm looking on my bookshelf because I'm blanking on the name. I will mention in the class book by Soulsby on sediment dynamics, which is definitely a must-have. I apologize, I'll bring that for you. And we have this relationship. Here you have the wave stress, wave-induced stress, current-induced stress, and this shows you what's the stress when you couple the two together. Here, this thing in brackets is basically how is TC enhanced. If tau W is equal to tau C, then the thing in parentheses here is 1 over, is equal to a half. And then we have raised to 3.2, blah, blah, blah. And it works out to this number here. So we get a 15% enhancement of the stress versus one of these alone. So this is the nonlinear interaction that we have. Excuse me. And 15% enhancement over just summing the two on their own. So is it huge? I wouldn't say it's huge. And for the nature of the game of sediment dynamics, there are so many places to have unknowns and errors associated with that. I don't get too excited about this, but it's a cool phenomenon, that is for sure. I'm going to show you one video just showing you the complexity. It's a numerical simulation. It's hard to visualize. This is a bottom boundary layer, just an LES simulation, and you'll see the actual kind of eddies. This is picking up at least the medium scale eddies here, the flow. So in this, if we actually have velocity probes, this is numerical again, but if this is visualizing a real flow, and we put velocity probes in a vertical direction like this, you'll see lots of fluctuations, right? Very, very fine scale fluctuations in the velocity. But if we average over time, you result in this nice turbulent logarithmic layer. So again, the flow structure in reality is extremely complex, disturbingly complex. But what we care about is what happens in the Reynolds average sense when we average over these fluctuations. So the fluctuations are important. They influence the stress, the resulting stress on the bed. However, in terms of, we don't need to understand their details for most work. What we're trying to get at is the sense of averaging over those, kind of time scales where we average over those are what are important.